Hello everyone. Today we're going to be doing section 9.3, which is about three formulas actually. The double angle, reduction, and half angle formulas. Right? Anyhow, as part of a summary of these three sections, which I normally would put together, it's just that I don't, it's going to be too long a video. Broken up into three videos, right? So, and over the course of 3 days. If, this is what we were doing last time, section 9.2. If you could take an angle and break it up into a sum, potentially, of two angles, which they usually refer to as alpha and beta, you could employ these sum or difference formulas. Or similarly, if you could break them into a difference, all right? What are they derived from? Right triangle trigonometry. Basically the rotation of an angle so that it is in, the initial side is basically along the x-axis, right, positive x-axis, and the distance formula. Right? These things, which we'll be discussing today, the double angles, are basically derived from the situation in which the angle alpha is equal to the angle beta. Right? Hence they are a double angle. It's like saying 2 times alpha, 2 times beta. But rather than use one or the other, they will simply just say 2 theta. All right. Okay. And you would use it in a situation where, you can get away with that, right? Where the angles are equal to each other. The reduction formulas are basically derived from double angle. All right. And they're used basically to reduce even powers of sine or cosine or tangent. Right. Before I go any further, what I should do is, again, refer to the handout that will be relevant for this. Right? You may already have this. Right? These are basically the remaining trig identities. Right? These were the ones that we discussed last time for section 9.2, the sum and difference of cosine, sine, and tangent. Right? And today we'll be discussing these, section 9.3, the double angle, reduction, and half angle formulas. Notice that you have a lot of options when it comes to cosine. There are 3 different incarnations of this, tangent. And then for reduction, notice that and this is a little bit hard to see, I'm reading it backwards again. Notice that the double angle, cosine of 2 theta, which is up here, is part of the reduction formulas, all right? So that's why I say one is derived from the other, all right? If a person can basically get the value of the double angle, all right, they could insert it into basically this formula for translating sine squared, cosine squared, and tangent squared respectively. Okay. Anyhow, do try to print this, all right, because it's a reference that you would need if you try any of the problems. Okay. And you would use this again to reduce powers of sine, cosine, and tangent from, say, sine squared into ordinary first degree sine, first degree cosine, first degree tangent, or anything that is an even power. So if you had something that was raised to the 4th, all right, that's really just 2 squared. All right, that's an exponent of 2 raised to a 2. All right. Half angles, all right, are themselves derived from the reduction formula of each of these trig identities. Okay. All right. And in this case, all right, you would use these if you have an angle that's given to you that happens to be half of one of the special angles. When theta is half of you know, 30 or 45 or 60, well, 60. Usually 30 or 45. So if you had 15, all right, and you had 22.5, something like that, it would be appropriate to use half angle formulas. 9.4, which is coming, all right, 9.4 would be what we'll do on Thursday, all right, is translating products into sums and sums into products respectively. Anyhow, it's enough to cover these three things today, how you would utilize them. Just remember, special angles are very important. Right? Use these half angles when the theta is half of a special angle. Okay. And usually what that means is 30 to 45. Right? Half of 30 is 15, half of 45 is 22 and a half. Okay. Let's see. Right, let me give you an example of each of these things as you would use them. And we'll get rolling here. It gets a little dark since it's been raining. All right. I'll switch on the light. Hopefully this is agreeable today. My blue ink has been giving me trouble. And I'm trying to erase. It's being better. I think it's just a different marker. And they're not permanent either. It really shouldn't be problematic, but it has been. Anyhow, here's an example to discuss double angles. Suppose you were given, I think that is showing up in the thing, it's kind of faint. I don't like that reflection. Yeah, like this. Suppose you were given the tangent of theta is equal to -3/4, that ratio, and the triangle in question, or the angle, theta, is in quadrant 2. Okay. The first thing I would do is basically draw a picture to summarize this information. Draw it. Okay. To summarize. So, here you have coordinate plane, y and x, and here is a circle superimposed upon that, and it's a badly drawn circle, but so be it. You remember that this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4 respectively. If we were to appropriately position a triangle, a right triangle, it would have to be in quadrant 2 according to these instructions. So you would have a simple triangle like this, tucked in here. Okay. Now the reason it's important to draw this picture is it would help you identify which one of these top of the bottom number is actually the negative. In quadrant 2, it's very specific, right? For example, your x values are negative in quadrant 2, but your y values are positive. When you have a tangent, right, remember that the tangent of the angle is the ratio of, if you're not using SOHCAHTOA, if you're using x's and y's, or r potentially, it would be y over x. That means that it's the x that is specifically negative in this case, right? Because it's in quadrant 2. Okay. Now, if I just enhance this, it's oriented like so, right? And we're talking about this angle theta. If you wanted to get the angle theta right now, all right, you could just perform the inverse tangent, all right? All right. But I'm going to use this to basically calculate a double angle, all right, without a calculator. All right. Use this to calculate the double angles without a calculator. Alright. Again, if you wanted to get the angle, right, you could easily do this, right, at this point. The inverse tangent of -3/4. Alright, and that will tell you what theta is. So you don't need the double angle formula to calculate that. Alright, you just want to see what the double angle of sine, cosine, and tangent respectively would be equal to without using the angle, alright, or, and this has not been told to you, or without using the calculator, because you don't actually need it. Alright, that's the whole point of this. You could use this to calculate double angles without a calculator. Anyhow, I'm going to continue to finish the appropriate labels. If it's a positive y, and this is really a 3 on top, alright, then that means that the dimension here is +3, right? And if this is an x on the bottom, and it is understood as having to be negative, this would be -4. Right? So that means that the dimensions here would be -4 respectively. All right. From that, you know that you can calculate cosine and tangent, which is what the double angle is going to involve anyhow. All right. Let me erase a little bit, because I got the information that I basically need. So I'm going to get rid of this. And then we'll choose the appropriate formulas, right, using this sheet, right, which was the whole point of having this handout. Okay, we're looking at 9.3. Here's our double angles. Let's calculate the double angle for sine. All right, it is 2 times sine times cosine. All that we need to do is basically figure out the one dimension from here that is still missing, which would be the radius dimension, right? And in that event, you really just need the Pythagorean theorem. Which, if I rearranged it to solve for r, instead of it being a squared plus b squared equals c squared, we change the labels to x, y, and r. C is the radius, that's the hypotenuse, c, r, all right, they're interchangeable. Then we would use this formula to calculate x squared plus y squared. Take a square root of that, right? Inputting these dimensions, right, +3 and -4, into the formula. All right, for x technically would be here is a -4, and for here is a y, all right, it would be a +3. That makes this really 16 plus 9, which is really 25. And if we took the square root of that, r would be 5. Now, when we consider the double angle formula, and I hope it's not too faint, the double angle formula for sine, it is established that this is 2 times sine of theta times the cosine of theta. All that we really need to do is insert what the ratios would be for each of these, all right, which means that this is going to be a fraction, and this is going to be a fraction, and this is still going to be a 2. All right. So sine is, let's use SOHCAHTOA. All right. Sine is the opposite of the angle, which means that it would be 3 on top over the hypotenuse, all right, which would be 3/5. Let's see. Yeah. Okay. And cosine is adjacent over hypotenuse, so adjacent to the angle would be -4. over the same hypotenuse of 5 rather. Okay. And then it's a matter of simple arithmetic. You know, if you have a fraction times a fraction, it's top times top. If you happen to have 3 of them, right, you can disguise 2 as a fraction by sticking a 1 under it. You can simplify if it's possible before you multiply. In this case, it really wouldn't be possible. And then see what you get. 2 times 3 is 6. 6 times -4 is -24. 1 times 5 is 5. 5 times 5 is 25. If we knew what the angle was and we doubled it and then took the sine of that, it would be this ratio. All right, -24 over 25, which is a decimal, is like 0.9 something. Let's see. 0.96, you would see. Now, it just so happens, I couldn't help resist the temptation. I figured out what the angle was, all right, before, all right, but just to prove a point, all right, put the cap on that before it goes flying. The angle is, the original angle is something like 36 degrees, all right, which again, if you really wanted to, you could calculate by inverse tangent. All right, just make sure that your calculator is in degree mode. Is the inverse tangent of the ratio, which would produce an angle. And you see it's -36.8, whatever it is. All right. If you multiply that by 2, all right, you'd have 73, you know. If you took the sine of that angle, right, -36, and there's a way to store this in your calculator if you've never seen it. I'll point to this. Here's this STO button, store, and there's behind it is recall in blue. If you wanted to store this, you could store it in any of the letters. See these green letters? So you could say store 3 divided by 4. You would press store, all right, the last answer that you had gotten, let's just say 36. And then pick a place where you want to save it. So if you hit alpha, that'll engage the letters. I like to put it in Y, but just because it's in proximity of the button here. That means that it is now in Y. That means that in theory you have at least 26 places to store information if you wanted to. Anyhow, now if I took the sine of 2 times that angle, which I will now recall, and I'll engage recall by hitting blue second first, and then recall, and then hit alpha and then 1 to get that letter, and then hit enter. It's 72, whatever that would be, or 73. And then close this. Look what you get. -96, which to scroll up here is what had been calculated. I did erase it actually. All right. Here, I'll do it again. That's using the angle in question. Here's what -24 divided by 25 is. 0.96. All right, the point is that you don't need your calculator to do everything for you if you have these formulas memorized, or at least have the reference to use them. All right, you didn't even have an angle given to you. I'm just temperamental and I wanted to know what it was. All right, but as long as you have the ratio that the tangent angle of the angle represents, you can determine where it's located. If they specify the angle, what the dimensions would be, negative or positive, and then infer what the missing is, the R, in this case the hypotenuse, via Pythagorean theorem, and then plug it into the double angle formula and it produces the ratio that it would be. Okay. I suppose in theory that if you were going to try to figure out the angle at this point, you probably could, all right? I'm kind of tempted. I hope you will humor me for a moment. If in theory you wanted to figure out the angle given this information, all right? And you know this is -24 over 25. in a similar way to, taking the inverse here to figure out what theta is, if you took the inverse of negative 24 over 25 and then divided by 2 to get rid of the times 2, all right, it should give you the same thing, 36 point whatever it is. So let's see, hypothetically, all right, the inverse sine of negative 24 over 25, all right, is inverse sine of the ratio that we have, all right, divide by 2 is the same angle, negative 36. Okay. All right. Let me show you the other ones. Sorry. And then we'll move on to the reduction formulas. When it comes to the double angle for cosine, I have 3 different incarnations of that to choose from. I'm going to go with the first one. I'm not going to do all of them. It would be silly, right? Here's cosine of the double angle. It's cosine squared theta minus sine squared theta, which you might go, geez, that sounds familiar. That's because cosine squared plus sine squared is 1. All right? And again, these are borrowed from the original identities, so it makes perfect sense, right? In this case, you're subtracting. So the cosine of the double angle is equal to this relationship. Right? Cosine squared of theta minus the sine squared of theta. And we already have all of our dimensions. We have 3 and negative 4 and 5, right? So we could, on the fly, input these where we need to, right? If you don't like the way that this is presented, that this is a squared trig function, remember, if it makes you feel more comfortable, you certainly can write it like this. Like that, right? Pushing this to the outside, they're equivalent, right? This is, I guess, a fancy way of writing, you might say. Anyhow, if cosine is adjacent, right, over hypotenuse, then what you would have in this case is negative 4 over 5 squared. All right, there's a minus in our formula, and in this case, sine is opposite 3 over hypotenuse. You would have 3 over 5, and then you would square it. Right. The result in this case, mix those. All right. Remember, when you square a fraction, you have to square both the top and the bottom. This is 16 over 25 minus 9 over 25, which means that cosine of the double angle is equal to 7 over 25. Okay. That's a positive. All right. Let me double check my signs. I'm not worried about that. Yes, it's positive. Okay. Okay, one more. Right. I'm running out of space here. So I'll erase what little I can. Alright, tangent. It's going to get messy, so let me erase this. Tangent of 2 theta is equal to 2 times tangent, yep. 2 times the tangent of theta sitting on top of the difference 1 minus tangent squared. Okay. All right. Now again, we have from our triangle established what the correct dimensions would be, so we can get the ratios fairly easy. In place of tangent, right, would be the ratio of y over x again, all right, which is something we already have, which is -3 over 4. All right, and in this case of tangent squared, the same thing, -3 over 4. Okay, so what we would have, right, 2 over 1 above the line technically, times -3 over 4. And then underneath you have 1 minus -3 over 4, the whole thing squared. And I'll just clean it up. Where's my blue? What to do with it? Oh, it's over here. Okay. Top times top, bottom times bottom, you have -6 over 4. In this case, you're going to square this first and this first, so it means that you end up with 9 over 16, all right? And it's going to end up being positive overall, because you're squaring a negative. There's a minus in the formula, so do be careful. You will subtract, all right? When you have a whole number 1 here, just borrow what the denominator is here and convert 1 whole to so many 16ths. So it would be logically 16 over 16, all right? And then when you subtract fractions, it's 16 minus 9, which is what, 7 over 16? Okay. Now you have a complex fraction. Remember, when you have a complex fraction, it's just one fraction sitting on top of another. Right? If you feel more comfortable, write it sideways, sort of more horizontally. -6 over 4, this is division, and then it's 7 over 16. And then there's the old arithmetic rule, right? Keep, change, flip. Which means you're going to keep the first fraction exactly as you see it oriented. Change this to multiplication instead. And then use the reciprocal, which is to flip this fraction upside down. So if it's 7 over 16, it will become 16 over 7, right? A practical thing would be to try to simplify, cross-simplify, by using a common factor first rather than multiplying first. That is, again, if you're not using a calculator. All right, so you would notice that there's a relationship between these two things potentially. 4 and 16 are both made of the same factor, 4. So you could reduce them by that before you multiply. All right. 4 divided by itself is 1, 16 divided by 4 is 4. All right. And then you have -6, negative top times top here is -24, and 1 times 7 is 7. And though it's an improper fraction, that's what the tangent would be. Okay. Okay. All right, so you got -24 over 25 for sine, double angle. Tangent is this, 24 over 7, and the cosine double angle is 7 over 25. Okay, sorry for the sloppiness. I do wish my board here was a little bit longer. Let's see, I just want to double check something really quick because I'm paranoid. Good. Okay. Yeah. I was just worried about the sign, but that is positive, so it's correct. Good. All right. All right. Again, so why do we care about the double angle formulas at all, aside from being able to prove to ourselves, yes, we can do this without a calculator. All right. It's part of the reduction formula. You will see now. Double angles. The reduction formulas involve a double angle. Right. And we care about the reduction formulas ultimately because of the half angle formulas, which are useful in calculus. Dirty board. Let's erase it somewhat. All right. let me point to these again. All right, the reduction formulas are next. And again, you see when you have degree 2, these are sine squared, cosine squared, and tangent squared respectively. Each of these involves, the double angle for cosine in tandem with the other features here, subtracting and then adding and subtracting a ratio over here. So if you have a double angle, right, you could insert this in theory into the reduction formula. All right. All right, more practical than that would be even to use this, right, to reduce used to reduce even powers, right, of sine or cosine or tangent in theory, meaning degree 2, degree 4, you know, in which case then you could reduce it to something that is degree 1. Right? That's usually, I mean, right off the bat, that's what it translates from. Something from degree 2 into more or less the normal degree, degree 1. Regular sine, regular cosine, regular tangent. Regular. So it's all boring, right? Okay. Right, so here's an example. Right, suppose you had to rewrite cosine to the 4th of x, right, in terms of the first degree. I just call it regular cosine for lack of a nicer expression. Right, we would employ the reduction formula, not double angle. Reduction. Sorry. Losing my mind here. Reduction formulas. We're going to reduce even powers. I'm sorry, I'm losing my mind. Alright. Wake up. I don't have enough coffee today, apparently. Okay. So, given this task, I'm going to zero in on which of these. Cosine squared, all right, is 1 plus cosine of the double angle divided by 2. All right. What we have here is something that's cosine to the 4th. All right. But just realize, if I were to take this, all right, and first of all, I'll put it here. All right. I'll just move this to the outside. All right. What I can do is, no, I don't want to do that. I mean do this, right? This is the same as if I had this. Cosine of 4 could be written in the style of squared cosine, but something squared being squared, all right? Basically, an exponent raised to an exponent. Okay? And if that is the case, right, just pay attention to the inside guts here. We could go ahead and use the cosine incarnation of reduction formula. So, I'll put this in red just to be somewhat consistent here. Cosine squared of x, right, instead of theta, it doesn't matter, right, is just this, right. 1 plus cosine of the double angle over 2. All right. It's still, mind you, because of the nature of this being really the 4th degree, something that is being squared. All right. So although yes, the innermost parentheses here is really just, well, this parentheses here is just cosine squared, and translate to this. Bear in mind that later on, we're going to have to square our results once we straighten this out. The formula uses theta, all right, instead of x. So I'll just translate this into 2x. Let me get rid of this so I can use the space. And there's my blue being a pain in the neck again. Life's so nice, but it's such a pain in the neck. I have two different, I have actually several different markers that are blue. And they start out great, but then they get worse and worse. Let me use this one. All right. So, let's take this apart. Okay. We have established this, I'll just put this up here, that this is really cosine squared of the angle itself squared. And in place of that, I'm using the equivalent here according to the reduction formula. Squared. And now, let me move this. Let's distribute, well, let's square what we have to square, right? The entire top of this, you can treat this as though it were a fraction, would be affected by the exponent here, all right? The entire bottom, which in this case is just say only 2, would simultaneously be affected by the exponent 2 on the outside. All right. Again, why is this here? Because when you have an exponent raised to an exponent, they multiply, and that's what it was, 4 to begin with. So, what you end up with is this. 1 plus the cosine of the double angle squared sitting on top of 2 squared. And the bottom is really easy, right? 2 squared is just 4. Right? But this is going to produce what you might remember is the perfect square trinomial. Right? When you have identical, I know this cannot officially be called a binomial, but you see that it has 2 distinct terms here. Just one happens to be a transcendental function, cosine, rather than an algebraic function, but it still is going to behave like this, right? Which means that in theory, if you have that memorized, the perfect square trinomial, the outcome of that, and I'll just put it here for reference, right? It's going to be, according to the model, a squared plus 2 times ab plus b squared. You could, recognizing that this is a and this complicated quantity is b, right? Insert them into the model and you can get to the answer a little bit faster. But even if you don't know that, just do what is intuitive, right? If you have this being squared, then you have essentially 2 iterations of this, 2 clones, right? Of identical factors. So you have 2x, right? And you have 1 plus cosine of 2x, right? And mind you, this is still sitting on top of 4, all right? And then at this point, you would FOIL it. 1 times 1 is just 1 squared, which is just 1. 1 times cosine is cosine of 2x. Right? You can put a 1 in front of it if you like, right? Just like you could put a 2 here if you like. It's the same difference, same outcome, I should say. This times this is yet another of these, cosine of 2x. And then cosine times cosine is abbreviated by an exponent of 2. So plus the cosine squared of 2x, right? All sitting on top of 4, right? Again, if you know the model, if you feel comfortable with it, all right, then you can go directly to the result that's going to happen here. You have two of these, all right, that are identical. They're like terms for all intents and purposes. One cosine plus one cosine is two cosines, whatever the guts are, if they happen to be 2x. All right, so just going back here for a moment, because I need the space again. You now have this, all right? 1 squared is just 1. 1 and 1 is 2, with a cosine 2x attached to it. And then you have this hanging on here. Plus cosine squared of 2x. All right, all sitting on top of 4. All right. All right, now it just so happens that spitefully, you could reduce this a little bit further, because tucked inside the result here, all right, of essentially formulating the binomial-esque looking 1 plus cosine 2x, is that you have something that is the regular sort of incarnation of this, cosine squared. We started with cosine to the 4th. All right, but again, the point of reduction formula is that you take even powers, like 4, and you reduce them, all right? So we could do it again, right? We could reduce according to the formula again. You might be going at home, yippee-yahooey. But it will work, you'll see, it just gets more and more expanded. Give myself a good amount of space. Blue is a pen black. Alright, so what I'm going to do is, in place of this last term that just coincidentally is the same thing, the cosine squared of a double angle, instead of theta, it's, instead of 2 theta, it's 2x, right? I'm going to fit the equivalent according to the reduction formula, right? All right. So what do we have? 1 plus the cosine of 2x over 2, fitted into here, still sitting on top of 4, still added to these other features here. Okay. And then straighten this out as best we can. Now what we could do to sort of kind of clean this up a little bit is now take advantage of the denominator that is a common denominator of 4. Kind of move it from where it is up to the front here. I'm going to sort of factor it into each of the parts. So if I rewrote this like so, if this was a denominator, and I'm just going to push it to the edge here, it would look like that. Right? And then there's still all this interesting stuff in here. There's still 1, there's still 2 cosine of 2x, there's still what we have here. 1 plus the cosine of 2x over 2. Right. The whole objective, remember, not to get away from it, was to take something that was a degree 4 and make it exclusively into things that are degree 1, all right? That's why I'm bothering to reduce this a second time, all right? Anyhow, I want to expand this as much as I possibly can. What I really should do is try to straighten out the guts in here now, all right? So then more or less along the top tier here, all right? In other words, let's get rid of the fact that this has a denominator, you know? All right. If I separated out these two terms, they would both have the common denominator. So over here, I'll write that, just as I'm running out of space. 1/2 onto itself, all right? And then 1/2 times cosine of 2x. Right? And again, I need a space. So I'm going to go all the way up to the tippy top here. One more time. And write out everything I have. I got this 1/4 here. The inside of this, which I'm going to use as a bracket instead of what it is. This is going to be a lot of stuff with parentheses. 1 plus 2 cosine of 2x. All right, and then this stuff that is in blue. All right, plus a half. Because it's plus times a half plus times that. That's a half cosine of 2x, all right? Now what I will do is distribute this quarter to each of the terms here, one by one, right? 1 times a quarter is naturally just a quarter. Okay. And 1/4 times 2 is a half, because it would end up being 2 over 4. So 2/4 is really a half. All right, with a cosine attached to it, 2x. 1/4 times a half, now notice the 2 is a denominator, is 1/8. So a free floating eighth, if you will. And then in this case, it would be times the similar feature of 1/8, but it's a coefficient, right? So you have that, right? I can now at this point combine the little that I can, which are the like terms that are regular ordinary number, 1/4 and 1/8. Right? If you do that, right, just remember fractions have to have a common denominator. Upgrade this to so many eighths, right? 1/4 is really 2/8, right? Because 4 times 2 is 8, so 1 times 2 is 2. Add 2/8 to 1/8, right? And we'll stick that up in the front. Blue. So what do you end up with? 3/8 plus 1/2 cosine of the double angle, just calling it x instead, plus 1/8. I made one boo-boo. I would at this point attempt to combine the cosine of 2x and 2x because they are like terms, but I can't because I actually made one slight mistake here. I'm sorry. Anyhow, what happened earlier should have been this. I really need to learn to check my notes as I write stuff. All right, when we reduce this term, all right, cosine squared of 2x, all right, what ends up happening, and it is a little bit easy to see if you think this of 2x as just being theta, right, is that you would get this, right, 1 plus cosine of 2 theta. It just so happens that, and this would be over 2, theta at this point in the problem is already 2x, right? So in place of theta, I would need to have inserted 2x, which means that this here is really 4x, right? Sorry for that. This is why, again, not to make too many excuses, but better to write what your thoughts are. If you're tempted to do this in your head, it'd be easy to make a mistake. But if you write something and you go, oh, you eventually catch yourself, right? If you learn from anything, learn from the example of you should look at what you wrote, right? Write things and then double check them, right? Now at least I can fix it, right? So anyway, at this point when we were basically reducing for the second time, all right, the formula would be 1 plus cosine of 2 theta. It's just that the argument here was 2x to begin with. So it's basically 2 times 2, right? That's why this is 4, and that's why you can't combine these. Right? This is really 4x. These are not like terms. If they were 2x and 2x, then yes, I would attempt to sort of compress this together. All right, but this is the end result. All right, 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. All right, that comes from reducing twice. You have to. If the whole objective of this is to translate something from power of 4, the fourth, I should say, to, all right, first degree, or first power, you could say, all right, then that's what you end up having to do, reduce twice, okay? All right. All right, now let's get into the half angles. Let me show you 2 incarnations of that. All right. Let's do a more practical thing for a moment. Let me clean this up because it's pretty bad. The blue does not want to go away. Okay. So, get a little spritz in. Helps a little bit. Alcohol is actually better. One would think that the spray that comes with the markers would be more effective. It's not. Anyhow, that'll have to do. I don't like that. I'm gonna keep it like so. I should have stopped raining. All right, here's an example that discusses half angles. This is a little bit still wet. Let's say that you would, and again, this would be more practical. All right, if you had to find the sine of 15 degrees, all right? Yes, you could use a calculator, and it would give you a high degree of precision. That would be some decimal number. All right, but you don't have to, and that's the whole point. All right, let's find. You don't have to use a calculator. Let's find this sine of 15 degrees using half angle formulas. You want to use, again, half angle formulas. My thing is fading out. You want to use half angle formulas, all right, when you have half. I want a nice marker. No, that will suck. Half of a special angle. All right, and you know the special angles are in general 30, 60, 90, right? And 45, 45, 90. But since, you know, half of 90 is 45 to begin with, that is so faint. Give me that. Is that dying? Yes, that is dying. That one's going away. Okay. Let me see if this one writes any better. Well, kind of faint. I like red, but unfortunately it's not behaving either. Anyhow, realistically, where would you use this? All right, when you have half of 30, which is 15, all right, or when you have half of 45, which is 22.5. Okay. Half of 60 would be 30, right? Half of 90 would be 45. All right. So again, to refer to the handout. Right. Now looking at the half angle formulas next to the triangle lady here, we have the sine of alpha over 2. That is half of whatever the regular angle would be, the special angle. Right. It's kind of funny how you think about this. I mean, if you think back to section 9.2, right? A lot of times you start with something, you know, for the sum or difference formulas, where you don't see explicitly some angle plus some second angle. You have something given to you. Like, I'm trying to think of something nice. It's like 75, you know? And you take the number 75, and if you could conceive of it as not just being the number 75 by itself, but two things added together, right? Then you could take advantage of the sum of the angles, right? What is 75? It's 60 plus 15, you know, something like that. Or perhaps a difference somehow as well. Anyhow, it's kind of like that in this situation as well, where you see that you have something given to you, right, in the formula as a regular ordinary angle, but it's being divided. That's more or less what's happening here, right? It's one of these disguised. Which one specifically? It's 30, really. Anyhow, if this is, we're using sine, we use the half angle for sine. The sine of half angle is officially the square root of 1 minus the cosine of the angle over 2. All right. We could calculate this without using our actual calculator. All right. We can get an exact value. All right. Not something with just a high degree of precision. Okay. All right. So let's start with this. All right. If we want to figure out for 15, we have to think of this as being 30 divided by 2. All right, how come? Because in the formula, it's really the cosine of 30's ratio that we would employ at this point. All right, so remember your special right triangles. 30, 60, 90 would be the appropriate one. And if you have the square root of 3, it is always along the edge of the 30. And 1 is along the edge of 60, and this would be 2 for the hypotenuse. We could choose the appropriate dimensions to substitute for the trig function. So the cosine of 30, all right, what is cosine? It's adjacent over hypotenuse, realistically. Nice and red, come on. So what's adjacent to 30? Square root of 3. What's the hypotenuse? 2. We're going to use basically the square root of 3 over 2 in place of this trig function of 30 degrees. Okay. And mind you, this is still underneath the square root. This is still being divided by 2. Right? If we can help it, and we will, it will work out nicely, I promise. We're going to try to reduce the guts here of the radicand, right? The inside of the square root. So in order to do that, let's reduce the top to just one sort of ratio, one fraction, and then we could employ, regular ordinary division here. If this is a denominator of 2, then we could translate the 1 whole into the equivalent to using 2's. It would be a ratio of 2 over 2 is still 1. Right? And that means what? The top would be 2 minus the square root of 3. Hopefully that is visible. It looks like it is. All right, sitting on top of the common denominator here, which is 2. And then this is still itself sitting on top of 2. Okay, and this is still underneath the square root. That's the downside to cleaning the board, I guess. It destroys your markers right after. Okay, I need the space, so humor me. I'm going to put this over here. So, if you think of this now as being one, I thought what's ugly on top here, it's just one fraction on top as it has this common denominator. This is dividing then by 2, right? What I could do is take this and sort of, see how it's sort of stacked on one another, translate it to that's a little bit more horizontal. So you might say that this is really 2 minus the square root of 3 over 2 divided by, what's the denominator? 2, right? And in that respect, since it really is, although it's ugly, right, it's an ordinary sort of division problem. We're going to employ keep, change, flip, right? Once again, right? And this is still going on underneath the radical. Okay. Keep this as you see it. Change the operation of division to multiplication. And then flip this to its reciprocal. If it really is whole number 2, then it's technically 2 over 1. If that's flipped, its reciprocal would be 1 over 2. All right? Which means that, and now would be top times top, which if it's just 1, you could just write this as 2 minus the square root of 3, exposed. All right? And then bottom times bottom is just 4. All right? And again, this is still going on underneath the square root symbol. Right? Now, at this point, all right, what we can do is take advantage of, from radicals, right, the quotient rule. Right? Quotient rule for radicals, and this is radical, right, dude, is you just separate the top from the bottom, right? Give them each their own radical rather than one. And then you would have this, as ugly as it is, 2 minus the square root of 3, both of them underneath this radical still. And then the square root of 4. What's the advantage of doing that? At least part of it will escape the radical because the square root of 4 is just a regular number, it's 2. Right? So what do you end up with? This square root of 4 is just 2. Right? So what does that mean? The sine of 15 degrees is equal to this relationship. Whatever 2 minus the square root of 3 is, over 2. Notice that that is no longer in the radical. And just to prove it to you, I will validate with the calculator now. Right? I hope that's not too faint. Okay. Pretty ugly, right? Let's get the decimal equivalent just to see that it's true. If you're using your calculator to prove that this is just going to be whatever sine of 15 is, let's do what sine of 15 is first. I have it in degree mode. Sine of 15, you see that you get 0.25, whatever it is. When you're entering this, all right, be kind of anal retentive. You're trying to avoid a syntax error. Right? This is the top entirely, right? I would purposely write parentheses as that is I would type them because you don't want it to think that 2 down here is part of this. It's an afterthought. It's dividing last. All right, so I'm going to enter parentheses, square root. All right, again, how do you get a square root? Second, and then you see this behind x squared. And you're going to have a lot of junk under here. 2 minus, and again, avoid a syntax error. Don't use this button for minus, use this button. Then another square root. 3. All right. Notice where the arrow is. It thinks that you're going to keep typing under that particular innermost radical, so move out of it. and then move out of the bigger one, and then close the parentheses. Now hit division, and divide by 2, and enter, and you see you get the exact same decimal. Okay? Now again, it's an ongoing debate, and I don't want to belabor the point too much. Right? Why does anyone go, what do you bother with that? You know, I could just do this, right? It's true, right? But the advantage to this is that this is exact, right? Square roots, radicals, right? They don't give you a warm, fuzzy feeling, understandably so, right? Because we live in a world where, you know, everything is decimals, right? Even money is decimals, right? But even though this can give you something that is a very high degree of precision, all right, it's never going to be the exact answer because it has to in order to involve it in some kind of calculation, all right? It's going to have to round at some point, all right? So better, if you have irrational numbers like square root of 3, square root of 2, one inside the other no less, you would prefer, and say, for the sake of exactness, all right, something that doesn't involve a decimal. All right, and the formula allows you to not involve the decimal. All right, here's the last thing. It'll be another half-angle formula, but it'll be a little bit more like the problem that I started with, where you have to sort of, you give in a ratio, and you have to pluck out some information that's not explicitly stated by drawing a picture. Dry. Right. Suppose you are given is it the same problem? Yeah. Okay. Suppose you are given this much information, that the tangent of alpha, that's an alpha, not a delta, is this ratio. It's 8/15. All right, and the angle is in quadrant 3 now. All right, again, get in the habit of drawing a simple picture to summarize. All right, this is quadrant 1, this is quadrant 2, this is quadrant 3. So we would need to have a triangle in theory that is tucked in here, right? Always perpendicular to the x-axis. Okay. Why do we care? Because, all right, that dictates that this is a negative x dimension and this is simultaneously a negative y dimension, right, in quadrant 3. So if we are going to involve cosine, right, or sine potentially, in a problem that requires that, you're going to have to consider these as being negatives. All right. All right. Now, what is tangent in general? This is fading. Tangent in general, right, is the ratio of y over x. And if we're calling this 8, that's what y is. And if this is x down here, then this is what x is 15 and y is 8 respectively. All right? So it would be negative 8 and it would be negative 15. All right? Which is why it ends up being positive overall. Right? It's a negative divided by negative is positive, right? Okay. The only other dimension that's missing is what the r dimension would be. Right? So what we will use is the Pythagorean theorem. Right? You know, the trig incarnation of that, which is, well, not the one that involves sine and cosine, but instead of a squared plus b squared equals c squared, x squared, or you could put what y would be like, y plus x squared, y squared plus x squared equals r squared, right? Rearranged to solve for r, is r is equal to the square root of the y value squared plus the x value squared. Okay, so we stick, technically it would be -8 in here, and technically -15 in here. -8 is being squared, so it's 64. 15 squared is 225. And they're being added. 225 plus 64 is 289, something like that. 9, 8, yes, 289. R is equal to the square root of 289. The square root of 289 happens to be, well, 289 happens to be a perfect square. It's something in theory you can memorize. It's 17 times 17. All right, so the R value is 17. And I'll put that in the drawing. Okay, so we have all of our dimensions at this point. All right, now, if we are given this information, we can find the exact value of sine of the half angle. Right? That is, again, not using a calculator, using the formula for half angle. All right, for sine specifically. All right. Anyhow, I need the space, so what I'll do is I'll erase this. And write the formula, and we'll fill in the appropriate ratios. So if that's dry enough, it's good enough. All right, so here we go. Sine of alpha over 2. Again, we don't know what the angle is, we don't need it. We just need the formula. Half angle is, again, square root of 1 minus cosine of alpha, the whole thing over 2. All right. What is cosine? Cosine is adjacent over hypotenuse. So in theory, this is alpha in here. All right. What's adjacent to the angle? 8. All right. Wait a minute, is that correct? Oh, I wrote it over here before correctly. Tangent of 8 over 15, all right? I have to make one adjustment because I'm a dodo. Is y over x, all right? This is y, all right? This is x, these are backwards, sorry. 15, 8, all right, ding dong, all right. So, the cosine is my aunt that always comes to visit me while I do math here. Going up the wall. Hello, aunt, all right. I wish you would catch my mistakes, all right. Cosine of the angle being here, is adjacent, all right, it's an x value. All right, so what is that? It really should be -15. I'm sorry, I wrote it backwards. -15. What's the hypotenuse? 17. Okay. So again, we're going through the process of sort of cleaning up the inside radicand guts. That means that in place of cosine of the angle, we have this. 1 minus -15 over 17. Okay. There isn't much you can do with this immediately except straighten out that there is a double negative here. Sitting on top of 2. So this is really 1 plus 15 over 17. And then combine the top as best you can by taking advantage of a common denominator. This is 17 over 17. Once you have that, right, add 17 over 15 and you get 32, which makes this 32 over 17 divided by 2. And then write it out more or less horizontally. So 32 over 17 divided by 2 is the same thing as saying 32 over 17 times 1/2. Right? Right. And then it would reduce. Let's see. You could do 32 times, what is 17 times 2? Just curious. 34, right? Or strategically simplify first, all right? Which is 32 and 2 are made of the same number, 2 namely, so you simplify the 1 and 16. That means that the end result of all of this work is this. The square root of 16 over 17, right? If we can now apply good etiquette to this, which is to reduce the end result to something that doesn't have a radical in the denominator, rationalize the denominator, we should. So let me erase this as I need the space. Okay. So we have this square root of 16 over 17, and now we're going to rationalize the denominator. Well, let me factor it first. Let me apply the quotient rule. The quotient rule says that if you find it more convenient to do so, if you can't simplify this inside, then break it into 2 pieces. Right? They each are under a radical independently. Right? Now you have bad etiquette. You have a square root of 17 as a denominator, which in the days before a calculator is very annoying. So we will rationalize at this point the denominator. Right? When you rationalize the denominator, just to remind you, essentially what you're doing is multiplying by a convenient ratio of 1. And usually what that means when it's just a monomial term sort of here, it's really not a polynomial per se, but it simulates that. The convenient ratio of 1 is basically duplicating what you see here, since it's a square root. So if you see square root of something, write square root of that thing, and then put it above itself. Because no matter how ugly or complicated it is, if it's an irrational number, square root of 17 is, I don't know, 4 point something into infinity. It's something divided by itself, so it's still 1. All right. The effect is this, that you end up with the square root of 17 squared. And on top, square root of 16 actually escapes the radical, it's just 4. So this is 4 times the square root of 17. All right. And finally, this would be 4 square root of 17 sitting on top of just 17. This would be considered the best answer, right? Because it is both exact and rationalized. No radical in the denominator, okay? Anyhow, you could get that value even in spite of not knowing what an angle is. All right. That's it for today, all right? For homework, you're just gonna have to, like I said, you print this out, this reference, a different formulae. All right, and do section 9.3. I'll give you specific problems to do in my open math. Okay? All right, I'll see you guys on Thursday.